Wednesday seminar. So the first speaker is Christopher Hoffman.
Well, thank you for the opportunity to speak here. So I'm going to talk about universality and self-organized criticality. And this is going to be joint work with my old student Matt Young and my should-have-been student Toby Johnson, who are both at CUNY now. And this story starts back in 1987, which happens to be the only other time I was in England. But back in 1987, there was a paper by Bakhting and Weisenfeld on self-organized criticality, where they introduced this concept. And what were they trying to do? They were trying to, well, they were pretty ambitious. They were trying to explain everything. Per Bach titled his book, How Nature Works. So he was pretty grandiose in his thinking of himself and his work. But they were trying to describe models where there was energy which got gradually built up and then suddenly released. What would this be? It could be something like plate tectonics, where you've got two plates here, and then they start cranking against each other, and that happens very gradually, and then all of a sudden you get an earthquake and it slides and that energy is released. Or it could be an avalanche where snow is being added to the mountainside continually, and which is the potential energy, and then sometime it gets released into kinetic energy, or forest fires, things like this. And what were the characteristics that they saw in all of these systems? They saw that not only were we adding energy slowly and then occasionally quickly releasing the energy, we saw that the scale of the release of energy happened kind of on a very wide range. So you could get a very small earthquake. I had one last year where the only reason that I noticed is that I had some wine glasses hanging upside down, and then I just suddenly saw them start to move a little bit. And there was a 3.0 earthquake, but if you get a bigger earthquake, then you can't help but notice it. So you get these things that happen on very large scales, and these systems kind of, they tune themselves. The theory they had was they tuned themselves to a critical value. There's no critical value that's kind of going to be inherent in our systems, but they somehow will be tuned to a critical state. And they had the following thought experiment, and they said you get a table like this here, and then you just start adding grains of sand to the table. And then what will happen? Well, for a while, the sand will just start piling up until you get a big chunk of things. And then when you start adding sand, usually nothing will happen or something very minor will happen. But every once in a while, things will slide off the end. And so this kind of naturally, the system naturally drives itself to this critical state where at any given time you could either have a very small change or you could have a much more substantial change. The example which I like, that I kind of see, is when I'm teching a file that I will make a little change, I'll add a little something, usually the page will remain kind of the same. Every once in a while it'll kick words down to the new line, or it'll add a new line, and then every once in a while you just add in one extra word, and then suddenly the whole paper gets moved, and what was on page 13 becomes on page 15, and you get this kind of, these very small changes can happen on any given scale. So that's the sort of thing that we're trying to describe. Now, so they had the following mathematical model, which they said kind of had all the right properties. So what we do is we will have our system, which will assign to every element of the integer lattice, it will assign a positive or a non-negative integer, and that will be the number of grains of sand that are at that point. And what do? We start with a large number of grains of sand at the origin. In this picture up here, we have 1 million grains of sand started at the origin, and then we do the following dynamics. We say if we have some z in the lattice with omega of z is going to be tell me how many grains of sand I have at point z, and if this is greater than or equal to 4, because I have 4 neighbors, then lower omega z by 4, raise omega of z prime by 1 for each neighbor of z. So if I have here, if I start off with, say, 8, 0, 0, 0 everywhere else, how does this system evolve? What happens is, okay, so I've got one site that has more than 4, so I take 4 grains of sand from that site, and then I move it to each of the neighbors. And then again, I've got one place that has more than 4, so I take 4 from there, and I distribute it to each of the neighbors. Now, and this is what was done here, except we started with 1 million grains of sand at the origin. And then we want to know what's the final configuration. It turns out that it doesn't matter what order I choose to do this in. If I have two locations that have more than 4 particles, I could do it in either order. I'm going to wind up with the same final configuration. Now, and this is what we wound up with here. And the different colors that you see tell you how many particles wound up at the origin. And then when do we stop? So we keep doing this. We stop when every vertex has less than or equal to 3 particles. So we call this stable. So, and this is the configuration that we get here. Now, so are there any questions about the model?
What happens if you have 4 and you get 4? Then you continue.
So if one gets...
If you have 4 in the center and 3, 3, and 3.
Yeah, so if you have... So if we could do a more interesting example. So you said we have 3 everywhere and then 4. So what happens is I have only one site that can fire, which one site with more than 4, so it goes to 0. Then each of these go to 4. And so then I get 4, 4, 4, 4. And now I have 4 sites. I say I can do this in any order. So, well, I'll do this one first. And so I'll say this gets 3, 1, 1. Oh, that should be, yeah, it goes down by 4. It goes like this. And then I do this. And then this one's going to go up by 1. This one's going to go up by 1. This one's going to go up by 1. And this one's going to go up by 1. And no, this one goes up by 1, which gets it to 1. And then I'm going to wind up with, what's the final configuration? It's going to be, well, the next configuration I'm going to get to is going to be 2, 0, 0, 2, 2, 2. And then I've got, and I need some more 1s. And now I've got one site that has 4 particles, and so that goes down to 0, and each of the 4 around it go to 1.
Is it easy to see that the order is not important?
Yes, it is easy to see, so if you see it in the right way. So how do you do it? First, you notice that if I have 2 sites that can fire, if I fire one of them first and then the other, I wind up with the same thing. And yeah, that's just easy to check that it's basically addition is commutative. I add 4. So you do that, and then you say, well, and so not only is the order the same, but also what is the same is the number of sites that the number of times that each site fired, which is called the odometer. And then say you did it, and you have some sequence, and I did it, and I have some sequence. They both will have the same odometer, and you have your sequence, and I have my sequence. The first one in your sequence must be in my sequence somewhere, because you had 4 or more particles at your first site. So my sequence stabilized, so it's got to fire at some time. Then I can just bring that one to the front, and that doesn't change anything. And okay, so now we have 2 sequences that wound up at the same thing, and the first terms are the same. And then you just inductively do this. So you can see quite quickly that the order does not matter. And that's really kind of one of the most important things about these systems, the only reason we can really analyze these systems. And somehow my screen turning off made these things very large. And then you can see, so there's some really, really beautiful mathematics that's associated with this. So in one way, this is really good. This was analyzed by Lionel Levine, Wesley Pegden, and Charlie Smart. And so there are connections between this model and spanning trees. And also the description they found involves some PDE. And they showed that the limit configuration is governed by some PDE. It's really, really beautiful mathematics. It produces these really, really nice pictures. Unfortunately, this beautiful mathematics means it's really bad for physics. Because what the physicists want to find is not a beautiful picture like this. What the physicists want to find is, so you can see that this is pretty close to a circle, but it doesn't look exactly like a circle. It's got that big flat edge on both of the sides. So what the physicists would like to see is something which is boring. Which looks kind of like this, where it's very circular. It's got uniform density throughout. The previous one didn't have uniform density because, you see, we get these large monochromatic regions. So these monochromatic regions, they all have the same number of particles here. So the blue one, I think the blue ones are 3 maybe. So you get a lot of these regions where the final configuration is 3. And they are these kind of triangular-like shapes. And so you get these huge seas of 3s and then some smaller seas of 2s, 1s, and 0s. And that's not what the physicists kind of think should happen in their self-organized criticality. So so what Bakhting and Weisenfeld thought was the universal model for self-organized criticality turned out not to be this model. What do they want to find? They want to have this be spherically symmetric. They would like to have a uniform density. They would like to have small changes in the graph equals small changes in the limit. So what does this mean? So this structure that we had before here, let's say we changed our graph slightly and we did Bernoulli percolation on Z2 first. So we go through and we remove 1 out of every million edges, just independent for each edge. We flip a coin, and if it comes up heads, 20 times in a row, then we remove it. If it doesn't, if one of the 20 flips is a tails, then we keep the edge. So we made a very, very small change to our graph. And all the structure that you see here gets wiped out if we make that very small change to our graph. So that's a result of a student of Charlie Smart's says that. So this indicates here that what we have is a system which has a lot of structure. The connections that it has to the spanning trees means that it has this mathematical structure, but that's not what the physicists want to see. So now what's the last thing is so I'm going to describe, in a couple minutes, I'll describe a couple variations of the model. And they all have some density. So if you look here, there's an average density of particles. I think it's 9/4 is the average density of particles. And what we want to see is that in any way that I look at this here, I should get the same density of any way that I look at the model. It's going to have some limiting density, and that limiting density is going to be the same for all the different versions of the model. So
by density you mean relative to the average degree of every vertex or something like that?
I just look at the area that gets occupied here, and then I want to average over that how many particles are there. So I just, over the places that get occupied, add up the number of particles, divide by the area of that region, and that will give me something. And so I'll talk more about what the variants are, and then for each of the variants, I will tell you what the density means. But in this case, what it means is I just look at the region that gets occupied at the end, and then it's just the average number of particles in that region. So that's what I mean. So this I call the point source model, where I start with a lot of points at the origin, and then I just want to look at, I want to say that the limit is some spherically symmetric ball with the appropriate radius, and it has the right, and so the appropriate radius, so given pi r squared times the density should be the number of particles. So, and it should be basically uniform density everywhere inside there. So I shouldn't have these regions here where I get more particles and these other regions where I get less particles. Are there any other questions? Okay, so basically what I want to see is this boring picture, which is just a kind of a constant amount of blue and white in all the different regions, and I get a nice sphere here, a nice circle. Okay, so what sort of models might have this? So the next proposal so I already told you that if I randomly break the symmetry by deleting a small number of edges, then that loses the structure. I'm going to talk about a different way of introducing randomness to this. And so I'm going to talk about the symmetric sandpile model. And here I will have that sites are unstable if they have at least 2 particles. In the abelian sandpile model we had, it was 4 before, but I could do that, but I will do 2 here. It really doesn't matter. I could choose anything I want. And then unstable sites fire 2 particles which perform which each perform 1 simple random walk step. So if my system looks like this, so I've got 1 unstable site here, and then this will fire, so that means I reduce the number of particles here, and I do, so let's say 1 goes to the left and 1 goes to the right. So then I get 1 here, 0 here, and I get an unstable site here of 2. Now next time they might both go to the left. Let's say they both go to the left and then they wind up here. And perhaps next time they both choose to go to the left again. And I get 3 particles there. Now I have 3 particles here, still only 2 of them are going to move. And let's say this time they decide to go in different ways, and then I get to the configuration here, 1, 1, 1, and this is a stable configuration. So unlike the previous model, the abelian model, which was deterministic, this model is a random model, and the configurations are, the stable configurations are going to be just 0s and 1s at every site. So there are questions about this model?
How to decide in which order the sites fire?
So again, it doesn't matter. So for the same reason it doesn't matter. So this is an important thing. They fire in a random way. So, okay, I'll give you a couple ways that I can interpret this. So, the distribution on the final configuration, so suppose the system eventually will stabilize. The distribution on the final system is going to be the same no matter what order you do it. That's one way of saying it.
What do you mean by distribution of the final system?
So so you want to believe that I'm always going to fire the particle on the left first. So I'll work on a one-dimensional system. You say I always want to choose the particle on the left that has two or more particles, and I will do that one first. You do this, and you get some distribution on what the final state is. I say I'm right-handed. I want to always fire the particles on the right first. I'm going to do this, and it's going to be some random, so the final configuration is going to be random. I'll have some distribution on it. You look at your distribution, I look at my distribution. It turns out those two distributions are the same.
There are certainly more general ways of choosing which particle fires first, and for any rule,
For any rule, it's going to be the same. And the reason is basically the same as it was for the abelian one. But so why is this true? So this is true because of what's known. So how do we prove this? We're going to look at the site-wise representation. So I'm going to have my randomness here. So I've got the integers. And so above each integer, I'm going to have a stack of instructions. What can an instruction be? An instruction can be, so there are 4 possible instructions. They're each going to be equally likely. An instruction can be left, left. It can be left, right. It can be right, left. And it can be right, right. Each of these have probability of quarter. And this is what the first particle does, and this is what the second particle does. I could consider these two the same if I wanted to. So above the origin, I'm going to have this set of instructions. So I have just this, for every integer, or for every vertex in my graph, I have a one-sided infinite sequence of these 4 symbols here. And what am I going to do? I'm going to, if I say, so my configuration looks like, so I've got 2, 3, 4. This is my initial configuration. Everything else is zeros. The first time that I fire this site here, the first time that I've got this site that is 2s, the first time that I fire this site, I'm going to look at the lowest thing on my sequence of instructions, and it says left, right. So I take one particle, and I move it to the left, and one particle, and I move it to the right, and then I get a 0 here. And then I cross that off. Now, here, I can choose either one of these here, and I get some set of instructions here, like this. And if you want to fire this one here, you're free to do it. If I want to fire the one on the right, I'm free to do that, but I'm going to use the same set of instructions. We're each going to use the same set of instructions. So I choose to do this one, which says left, left. So that means I take 2 particles away from here. They both move to the left, and they go there. you wanted to move the one on the left first, you're free to do that. They were right, and so then you would have done that here. At the end of the day, when we both finish, it's a finite system, so with probability 1, it's eventually going to stabilize. Then we're both going to wind up with the same configuration. It's not hard to check. It's a slightly glorified version of the previous thing. So not only are we going to wind up with the same configuration, we're going to have crossed off the same number of instructions. So I use those 2 instructions. We're going to cross off the same number of instructions at every site. So if I crossed off 3 instructions at the origin, so I fired the origin 3 times, then you, with whatever method you choose, which could be a random method, it could be a deterministic method, will have also fired the origin 3 times. So it's a function from vertices to the natural numbers, and it's the number of times that each site fires. This is independent of the method that you choose, the order that you choose to do this. It only depends on the instructions. And since it depends on the instruction, since the odometer depends on the instructions and the final configuration depends on the instructions, I'm going to have some distribution of it, but it's going to be independent of whatever method I have of toppling. Are there other questions about this? Yes?
Yeah, I mean, so not directly related, but what kind of initial conditions do you want to consider for this problem?
Oh, okay, I will answer that question, but I'll see if there are other questions first. That's going to be the next thing that I get to. Yes?
So, does this order of fires have to be independent with this direction?
The instructions are all independent. The sequences are IID, and each sequence is independent of each other. But the order that I choose it does not have to. I could always choose the leftmost one. I could always choose uniformly of all the ones that have multiple particles. There are all sorts of different ways that I could do it. They will all have the same final distribution on both the final configuration and the odometer. Any other questions? Okay, so so now I'll go back to the question about initial configuration. So there are a number of different ways that I could do this. I could, in this model, we started with a bunch of particles. I think it's, in this one, I think it's 10,000 particles at the origin. And then I just see what I get. Another thing that I could do is I could start with, I could work on a different graph. I could work on a torus. And I could just start with some number of particles on the torus and then go until it stabilizes. So what are the different possible things that I can have? So what are the variants? So the point source is the model we talked about for everything so far. So we just start with a bunch of particles at the origin. See what happens. So I could work on in ZD whatever dimension I want. And so then the critical value is the average density in the limit. It's not clear that that exists, but if that exists, that's what I'm going to call the critical value. Okay, I could have the torus. Well, so I could look on the torus. I start with a certain number of particles on the torus. Well, now average density is not really the right thing to look at because the size of the graph's not changing, the number of particles is not changing, so the density is just fixed. So what I want to look at is the fixation time. As long as the density is less than 1, it's not too hard to believe that this system can find some way of stabilizing, and it's a random process, so with probability 1 that eventually will stabilize. I could look at how long does that take. So, and it was probably gonna vary with the size of the torus that I'm looking at. And what I'm going to see is below the critical value, if the particles are not very dense, it's going to stabilize very quickly. It's going to stabilize in polynomial time. If the number of particles, well, if the density of particles is above 1, it's never going to stabilize. If the density of particles is close to 1, or above the critical value, it's going to stabilize very, very slowly because there are only a certain small number of ways it can stabilize, and it's going to take a long time to find that. So it's going to be polynomial stabilization below the critical value and exponential time to stabilize above the critical value in the size of the torus you're working on. The third system is called the driven dissipative system. This is going to be more like the initial experiment we thought about where we had a table and we were adding grains of sand to that table and things were falling off that table. So my graph will be, so my vertices will be in 2 dimensions. I'll just have a large finite square here. And what I'll do is at every given time, I will do the following 2 steps. So I have a stable configuration, which means 0, 1 particles at every site. I add 1 particle at a uniformly random location, and then I stabilize. So this is a Markov chain. And it's got it's pretty easy to see that this is nice, it's mixing, irreducible, and then I want to know what's the mixing time of this. So here, and okay, so this is one system. And finally, what's the last system? The last one. Yeah.
So when you say stabilize, so the particle go out? Or?
Yeah. So I'm working on a table. So
drop.
I'm a flat earther, and things get to the edge of the earth, they just fall off. They're never seen again. Okay, so I just do this. I add one part. So this is going to, now the density, and then I want to look at there's also going to be some average. So I guess there are two ways that I could look at it. I could look at the mixing time, or I could look at the average density. Either of those should be the right choice of the critical value. It should give me the same choice of the critical value. It could be the mixing time of this system, or it could be just I get some distribution on stable configurations. For each configuration, I find the density. I average that over all stable configurations, and that gives me a value for every n. I take some limit as n goes to infinity, and hopefully this converges. And then the fourth system is the infinite system. So I start off now with, say, a Poisson density of particles at every site, independent, and then I ask, and this is on Z2, and I ask how many, I ask, does the system eventually stabilize or does it not stabilize? And if the density is sufficiently low, then it will stabilize. If the density is high, then it will almost surely never stabilize. So below the critical value, the system will stabilize almost surely. Above the critical value, the system will not stabilize almost surely.
What does mean stabilize?
It just, every site fires only finitely many times. So,
Since the plane is infinite, somewhere
yeah, right. There will be some remote areas of the world where things are still going on for an infinite amount of time. But if I just look and see what happens in Cambridge, then eventually Cambridge stabilizes and it's good. Or if I see what happens in England, then eventually England, after some time, England will never change. And then for any fixed region I look at, eventually that will stabilize.
But this definition depends on the order of firing, or not?
It does. No, it doesn't depend on the order of firing. Yeah. So all the statements I made about things being independent of the order of firing for finite systems hold true for infinite systems. And if a site fires infinitely, so I eventually get to a system where there's only 0 or 1 particles here. So I have to fire every site if I have a 2. So if I have 2 particles here, I can't just leave them here and never fire them. I have to eventually fire them.
But is it not possible to decide that to take the decision which particle fires in such a way that
No.
all particles fire in the direction of the origin? So each time I have to choose some particle.
I choose some particle that fires, but then I don't get to see where they go. So there's no way to force them to the origin because they're equally likely to move away from the origin as they are towards the origin.
You have these rules about each side.
What? It just does not matter. You can look at the rules. If you know the rules and you want to choose the order, it's not going to help you. It's either eventually going to stabilize everywhere or it's not going to stabilize. Yeah. So you look at a set of instructions, and it will eventually stabilize everywhere it will. So these are the 4 critical values. And what we've, so the kind of one of the main conjectures in the field is that all these 4 critical values are the same. And in particular for the driven dissipative system, I want to look at the average density. I mean, they should all be the same, but for concreteness, I will say that we'll look at the average density. I would really like to tell you that my main result is going to be that yes, they are all the same, but the stochastic sandpile model turns out to be, since I have 2 particles firing at once, turns out to be kind of complicated to analyze. And there's the more recent model that people have proposed for self-organized criticality just has 1 particle firing at a site. It should have all these same properties here. And so that's the model that I want to talk about. So are there any questions about what the density conjecture says for 2 dimensions and the stochastic sandpile model, that all 4 of these critical densities should be the same? Okay, so this is the model that I'm going to actually be able to say something about. And unfortunately, I'm only going to be able to say something about 1 dimension. So I will restrict myself to Z as my graph for the rest of the time. I'd like to be able to say something about ZD for higher D, but right now we're only able to look at 1 dimension. So there are 2 types of particles here. There are 2 types of particles. They can either be sleeping or they can be active. Sleeping particles stay asleep until they're woken up, until an active particle arrives at that site, and then it wakes up. So active particles take simple random walk steps. I'll give a continuous time version of it here, but you can certainly do a discrete time version of it if you want. Take simple random walk steps with rate 1, and they fall asleep with rate lambda. So lambda is just going to be some non-negative number. Could be 0, could be infinity. So active particles fall asleep with rate lambda. And now, so if ever I have 2 or more particles at one site, so they all become active. So if I got two particles here, active, active, this guy's clock rings, it tells him to go to sleep, it goes to sleep, and then immediately I've got two particles here, and it becomes active again. And now, so what's a stable configuration? Stable equals all so all start sites either have 0 particles or they have 1 particle and it's a sleeping particle. So this model, this picture that I have up here is generated from activated random walk. It wasn't generated from the sandpile model. But as you can see, that if I look at this, and this is the driven dissipative system here, where I ran this Markov chain with activated random walk. Every step I throw in 1 particle, 1 active particle, well, either active or not active particle. I throw in 1 active particle and then I stabilize it, and I get a Markov chain. The density you see here it turns out to be basically the same density we saw on the point source model. That's what the density conjecture is, and it says that not only are the point source and the torus, do they have the same density, or the point source and the driven dissipative have the same density, but also the stabilization time on the torus and the critical value on the line. These all have the same density. So our theorem is for any lambda between 0 and infinity, activated random walk on Z has a critical value rho C of lambda. So this is the same for all. So you choose whatever sleep rate you want, which is some positive number. Then this activated random walk model has a critical value, and the critical value is the same for any one of these 4 models. And it's also going to be spherically. It's going to have the other properties we said the physicists want. It's going to be spherically symmetric. Well, it's a line, so the line is or a line segment, so it's going to be a line segment centered around the origin. But the density in any part of it, if I look at the left third of it, the middle third of it, the right third of it, they're all going to have about the same density. So I should say, so I talked about activated random walk, and when I introduced it, I said I could have sleep rate 0 or sleep rate infinity. So you might be familiar with those models. So sleep rate infinity just means that every time a particle gets to a new site, it automatically falls asleep. So the set of visited sites only increases, and I never have a site that gets visited and then becomes empty. That's just the IDLA model, so that's a very well-studied model. And the other case is when the sleep rate is equal to 0, so every time a particle gets woken up, it never falls asleep. And that is also a well-studied model. That's called the frog model. It's not nearly as well-studied as IDLA, but kind of on the extremes of activated random walk, we have two well-studied models. And what we're able to say, at least in one dimension, is we were able to prove the density conjecture, which says that no matter how you look at it, there is a well-defined critical value. So are there questions about this here? Okay, I see there's this nice big clock counting down, and it doesn't give me a lot of time left. So how do we try and go about proving this? The thing that I really want to understand. Yeah.
I'm a physicist, right? This looks to me like the Manor model, the Manning the Stochastic,
yes,
which is different from the SOC class that you started with, the Backtang Wiesenfeld class, right? We'd see this as being a representative of a different universality class among these models. It's a very interesting one, but there's a bit of a disconnect with what you said before. Or I didn't understand the transition from those models, which started off as dynamical systems with no stochasticity initially. This has, the stochastic rate lambda, and we would expect this to behave differently in ways that physicists are familiar with.
So the stochastic system, so if you have a stochastic system and a deterministic system, then they may behave differently. What we're hoping in this Manor model, which is this class of models that includes this system here, we want to show that basically these have the properties that Backtang and Wiesenfeld said that self-organized criticality should have.
Okay, I'm with you. Thanks very much.
Okay, so I want to, how can I have some hope of proving this? Well, the important thing that I mentioned is the odometer, so the odometer function, which is the number of sites, the number of times that every site fires. So I want to look at the point source model where I start with a bunch of points at the origin, and I see how many times does every site fire. This is, if I have a fixed set of instructions, this is a deterministic function. And there's something called the least action principle that says, if I can tell you some sequence such that if I perform a certain number of this number of instructions at the origin, this number of instructions at site 1, this number at site 2, then things will eventually stabilize. So I need that if I do this number of instructions at each site, that each site winds up with either 0 or 1 particles. And if it winds up with 1 particle, the last instruction that was done was a sleep instruction. So the least action principle says that this system is, the least action principle says that this is, the true odometer is the least of all the possible odometers. And that's the thing that we want to study. So it looks like people are very particular on time here, so I should have quit 20 seconds ago.
Okay, thank you very much. Any further questions?
Do you have any hope to do something in 2 or 3 high dimensions? Because I mean, they didn't look like Are you using anything really specific on the
yeah.
sort of exchangeability stuff? Or?
Currently we are. I mean, what we're using is we want to define some sub-additive process, and the sub-additive process that we're able to define and analyze was one-dimensional. The higher dimensional ones, I think I kind of know what they are now, but we haven't done any analyzing. I mean, basically, one dimension is really nice because if something spills out of an interval, I know it either spills out on the left or on the right. And no matter how big my interval gets, it can only exit on one or two spots. That's a really, really nice property to have. And I don't think that's essential. I think everything, I hope to come back here. I said the last time I was in England was almost 50 years ago. I hope to come back to England sometime in less than 50 years. I hope in significant less time than that we will have it done for higher D, but it's going to be a significant amount of work to do that.
Yeah, as you maybe know, I mean, the physicists, I mean, they like pretty much critical exponents, and that's, I mean, particularly at the time where this standby model were introduced. And one critical exponent which is interesting there is basically the one that describes the tails of the distribution of the size of the avalanches, which is quite clear in the first model that you described. I was wondering whether there are, whether you can define such avalanches. I mean, I don't know, in this last model, for instance, is there something equivalent?
Sure. I mean, you can. I mean, just if I look at, say, the driven dissipative system, where I've got this table here, I throw in one particle, and then I can say, how many actions did I do before the system stabilized? And then I'll get, it's a Markov chain, I'll get some distribution on that. And that distribution should converge as my table is getting larger and larger. That distribution should converge. It should have a tail law, and that should be the same tail law as I get for if any of these systems I can define that, then it should be the same.
Okay.
That would be. I know that's what the physicists really, really want to know about. That's what I would really. So I would really, really like to know that as well, but that seems, so Vindalin, I could give an optimistic answer to whether I have some hope of doing it. Figuring out the tail law or any sort of finer statistics on the limiting distribution other than density, those things seem much, much harder.
If you compare the empirical density with the average density, is it the case that with positive probability this will be a macroscopic amount?
Yeah, so we get some fluctuation bound that we get the chance that it's above any quantity. We get some exponential tail bounds. The probability it's above the critical density is decaying exponentially in the size of the interval, or below the critical value is decaying exponentially in the size of the interval. So yeah, we should get that, and we get that for the point source. We might not get exponential, but it might be some kind of some e to the minus some power into the power or something. But yeah, we get tail bounds on a lot of these things.